Hello, and welcome to Technically Speaking, where scientists and engineers come together to chat about a common interest, share knowledge, and satisfy some curiosity. I'm Laura, and in this episode, I'm joined by Emma to talk about the multiverse, the underlying physics, and why there are so many movies that feature it. So, to start off with, Emma, tell me something you know about this from your physics degree.
I haven't per se had a module in multiverses, but I've had plenty of modules in quantum mechanics, and I've had some cosmology modules as well. And as far as I'm aware, there are those two branches of physics seem to have their own theories on multiverses and, write them into the history and of physics and try and include them to make sense of things that don't make sense. But I think quantum mechanics is a good way to picture a lot of the physics theories of multiverses, because it's all about quantum mechanics and probability at the end of the day. And I think it's the most fundamental theory when it comes to multiverses. And there's many theories for multiverses, but one of the most popular ones, which also I think it's just come in and out of trends as well, because as I was reading about it, in the 70s, physicists weren't liking it, but in the 50s they were. And then in the 80s, they weren't liking it. And then now like people are starting to like it again. So now that it's trendy again, we'll go through the many world interpretation of physics, which is that whenever you make a measurement and you have different possibilities of results, there exists a universe where you have those different results come true. And Laura, are you following when I say measurement and results, or should I go through more of that?
I vaguely remember being taught about Schrodinger's cat and the thought experiments from my own undergrad degree. I mean, I did physics like 20 years ago now, and I think the way it's taught has probably changed quite a lot. So the measurement is essentially you interacting with the object or the cat in some way.
Yeah. So I'll recap Schrodinger's cat. I mean, I'm sure you know Schrodinger's cat, but it's the classic thought experiment of you put a cat in a box with a radioactive sample, and that if that sample decays and it causes a poison trap to release. I mean, there's many different ways that a cat can die in different theories of Schrodinger's cat, but essentially it's probability based, like the decay of a radioactive isotope. And then you close the box and you can't see the cat. And while you're staring at the box, you don't know if the cat is dead or if the cat's alive. So you say that it's both dead and alive as a superposition of the two final states. And that's where superposition comes into it. If anybody's heard that from quantum mechanics, it's something, two different states or multiple states happening at the same time, because you don't know. But obviously, if you were to open the box, you would see if the cat is dead or alive. And that's where like the results from the measurement. So the measurement is looking in the box in a case of Schrodinger's cat. And to relate that to the many worlds interpretation is that there exists a universe where the cat is dead and where the cat is alive, to put it in simple terms. And then when you make a measurement, you decide which universe you're in, which I think is a good way to think about it. It's a simplified version of it, but it's easy to digest, I think, which is important when it comes to multiverses.
A good analogy from real life is probably something like when you get your exam results and you get that envelope and you don't know what the results are until you open that envelope. So you could all have passed. You could all have gotten like 100% on every exam. You don't know until you look.
You both passed and failed until you see the results.
Yeah, and your life can go in any direction based on what's in that envelope, right?
Yeah. So I think that the many worlds has some sense, because you can physically imagine that because there are two possibilities, there is going to be a universe where that happens. It makes sense in my head. And it does seem to be more philosophical in that sense, because apparently when you actually do the maths, it's a bit lackluster of maths. So I don't think the cosmologists like that.
This is the bit where I start to become a little bit confused. I haven't studied maths in quite a long time, and it is all very maths based. It's all this theoretical stuff, isn't it?
Yeah.
The one thing that I remember from my undergrad that's maths based is if you have a particle in a potential well. And you can think of that potential well as a box that the particle can't escape from. If by potential, it just means amount of energy, right?
Yeah.
And it's got very low potential, so it can't really move from the space that it currently occupies. There was some maths you could do to try and figure out whereabouts in that potential well that particle was. But then some uncertainty came into play. You can know the position, but you couldn't know the momentum or something like that. And I don't actually remember any of the maths involved.
Yeah. You just mentioned Heisenberg's uncertainty principle, actually, the famous uncertainty principle. Yeah. So the potential well is essentially that. Like, imagine something's in a box, like an electron, with infinitely high walls, and it can't escape that box because the sides are infinite and they're solid and they're not moving. They become a boundary condition. And so when you know a boundary condition on a system, you can actually formulate a wave function which represents the state of the electron in the box. And I know I've said a lot of boundary conditions, states, I've said a lot of wave functions, I'm saying it all. But essentially, to break down what a wave function is, because I'm sure it's been mentioned in many films, probably in the wrong context as well. A wave function is any function like y or f of x is just a function that describes the state of a particle or a system completely. Like, it contains all the information you could need. So when you have a particle in a potential well, that has a wave function that represents it. And when you mentioned you can calculate the position and the momentum, you do that by performing a mathematical operation on the wave function. So if you wanted to say, I want to know what the position is, you would use the position operator, operate on the wave function, and then you get the probabilities of the position back. So that's a great time to stop because I've just mentioned loads of things.
Just throwing all the jargon.
Yeah.
It now sounds like we're doing surgery on an electron because you mentioned operations.
Oh, yeah. To make things complete, Heisenberg's uncertainty principle is you can't know the position and the momentum of an electron or of a particle to a great accuracy at the same time. You can't know both. You can only know one accurately, and another has to be less known. And there's that famous joke where it's like a police officer stops Heisenberg for speeding, and he says, "Do you know how fast you're going?" And then Heisenberg goes, "No, but I do know where I am." That's a bit of a classic one. All the physicists love that one. So with the jargon of operations, should I go over that a bit more?
I think so. So I'm sort of understanding it is you do some maths to the maths, essentially.
Mm-hmm.
So that set of equations that defines your electron, you can do something to those equations to give you some sort of information.
Yeah, essentially, it's all, if you think of it as like a broad like scope, it's essentially just probability theory. So the wave function gives you the probability of something happening, and you use an operator to determine what that something is. So probability that the electron's in the middle or average position, you perform the operation, and then you get the probability out of the wave function. Honestly, it's kind of harder to explain than it is to do the math.
I can imagine that because you're trying to visualize this thing that it's not quite accurate,
Yeah,
is it? You're not looking at like an actual, like a ball inside a box necessarily, which is the example
yeah,
we're sort of using. That's sort of as close as we can get to explaining it without just looking at some equations.
yeah. And because it all seems very mathy, and it is, you can actually simplify it, which does take away a bit of like the perfect accuracy of, the math, but that's what happens when you explain things. So it's not a quantum mechanically perfect example, but imagine that there's a wave function that describes a dice. So you have every information you want to know about the dice, where it is, what numbers facing up, etc. And so we could apply an operator that's called the what number is facing up operator. And then when we perform that on the wave function, we find that there's a probability of there being each number with a chance of 1/6, as you would expect. And that is a quantum mechanical explanation of something that's classical, though. So again, it's not perfect, but just to get like the idea of that you find, you know what you want to find, you apply it, and then you get the probabilities of the different outcomes is essentially what the whole maths of quantum mechanics is. And it's hard to understand. Like if you're feeling like, I don't know, if you're like scratching your head a bit right now, it's fine. Everybody's like that. Yeah, I'm doing a physics degree and I'm like that right now. So it's normal.
Fair enough, but I guess as long as you can follow your way through the maths and come to the answer that's on the exam paper.
Yeah.
I'm going to keep bringing everything back to exams and getting your results now, I think.
Yeah. I don't have to go through that for a while though, so that's nice. But yeah, so how does it actually apply to the multiverse? And it's the idea of the different outcomes that have different probabilities are exist in a different universe. That's so when you roll a dice and you get a 1, the many worlds interpretation is that you can have different universes with 2, 3, 4, 5, 6. But that's like just that theory. There's more theories that the like physical constants in the world are different in different universes.
Whoa, so physics is entirely different in that case.
Yeah, that's like the cosmology theory, which people are doing a lot more kind of research and maths into trying to find evidence for it. But it's what's known as the bubble theory of multiverses. And it's where the universe is split into bubbles and they all have like slightly different like physical worlds. So like the speed of light could be different in one of them because it happened at a different stage of inflation after the Big Bang. Again, many big words, but that's cosmology is different physics like backgrounds, and then I think the physics interpretation is just different universes.
See, I think I'm struggling a little bit with visualizing these bubbles in the universe where there is different physics, because that sounds like a physical thing that you should be able to interact with, because we're talking about bubbles, same as we were talking about a particle in a box before. But it's not what it actually looks like, because we can't see it because the physics is different.
Yeah. And also, I mean, that's what they're searching for. Like when I was looking into it, they were searching for gravitational waves or like evidence that there's like influence of different matter on our universe, which would be from one of these bubble universes, because they would also have mass and experience an attraction. That's how they're trying to look for it, I think. I mean, I'm not a cosmologist.
Yeah, but that would mean they'd interact in some way. So there must be some crossover from that different physics, that different bubble of physics to our bubble of physics.
Yeah, I guess it depends how thick is that bubble wall, like how much being separated from each other. But I don't know, maybe I'm a bit biased, but I like the different universes where different things happen, because that's where all the media and like Doctor Strange, multiverse, and like Spider-Man, you can have a different actor for Spider-Man in each different universe because that's a different outcome. So that makes sense to me. And I think that's what people like to hear about multiverses. Like no one wants to know if the speed of light's different. People want to know if Tobey Maguire's Spider-Man or if Tom Holland's Spider-Man. That's the real importance.
But I also made it quite easy for Doctor Strange to do certain things. That's basically what he was able to do. He wasn't doing magic, he was just doing physics.
Yeah, although Doctor Strange thinks that he can move between multiverses, and that has absolutely no like physical representation that I could find. Like there's no way to enter a multiverse.
Not even by something like quantum entanglement.
Physics words. No, I don't think, because quantum entanglement, it's nice to compare superposition and quantum entanglement. So superposition is when you have two states existing at the same time, like the cat being dead and alive.
Mm-hmm.
And then entanglement is when two states influence each other. And so that's what Einstein called spooky action at a distance, because he found that when something changed in one area, it changed something else. And so they were like entangled. And like the maths, when you look at an entangled wave function as well, you can see it. Like it looks like you can see that when you try and do the maths, it just doesn't separate. That's quite nice. So sometimes, if you guys don't understand quantum mechanics, maybe the thing to do is a mathematical course on quantum mechanics, and it'll just clear everything up.
I guess so. How much maths do you need to know before that? So like, I mean, before I went to university, I could do things like differentiation, integration. I vaguely remember doing stuff like Laplace transforms.
Oh, you mentioned Laplace then, and I was like, no. Not in quantum mechanics, actually. We did Laplace when we were doing about waves and stuff, but I think integration's a strong one, because you do the integration to find like the probabilities and things. But I think maybe if you only know integration and differentiation, I think you could get very far with quantum mechanics.
Okay. So that's the sort of maths that I'm fairly
Yeah.
comfortable with. I'd have to refresh my memory a little bit because I haven't done that sort of thing in a long time.
Yeah.
I do more real world things that don't even require me to differentiate and integrate.
Calculus isn't real world. No.
But I remember, again, when I was doing my undergrad, there was this big thing about grand unification theories and things like string theory and all these other things that
Yeah.
were like different aspects of physics that didn't necessarily quite match up, and that's what grand unification theories are meant to do.
That's one of the main problems with this many worlds interpretation is people don't like it because it's linear and the world isn't linear. It's not consistent with the theories that we have and we think we know now. And so people can't include it in theories. So that's why it gets disregarded. The maths of string theory, the theorists, they just, spend some time doing some maths and then they just get like, well, the universe should have 10 dimensions. And that's all I know about string theory, just 10 dimensions. But apparently there's like M theory, which is 11 dimensions. And it's this M theory that allows you to have different, they're called branes, but not spelt brain, BRANE.
Just to be more confusing, because it's not confusing enough already.
Yeah, different brains of the universe that can support the idea of multiverses, maybe. But I don't know how popular string theory is anymore.
So I was trying to get my head around it in preparation for this episode. And I got as far as, okay, there are 10 dimensions. The first four are sort of up and down, left and right,
Yeah.
and then moving through time. So the three space dimensions and one time dimension. And then the other ones were all like sort of almost like different iterations of the universe where something had happened at some point from the Big Bang to make things slightly different. And the further through the dimensions you got, the weirder things got,
Ooh,
essentially.
that's interesting. Because I saw some theories as well where there's multiverse theories where there was different levels of the multiverse. So like level 2 was the universe is having different physical constants. And then you have like, it goes all the way up, I think, to like level 4 of different like variations and different types. And then there's another theory with different types of universe. And then the many worlds is like what's known as a quantum multiverse. And you have like different like holographic multiverse that means different things. So I think people just like to kind of have an idea about it because also I think very funnily having 9 different types of multiverses, you have multiverses. I'm like, surely multiverse should encapsulate every universe. No, it's like some infinities are bigger than other infinities kind of like argument.
That does sound a little bit odd because I guess like, when you see it represented in films, it is usually like, a character has made a decision and then they split into two different timelines.
Yeah.
But it's still the same universe, it's the same physics. It's just one person decides to travel the world and the other one decides to stay at home and look after someone or something like that.
Yeah.
I guess because that's quite a human way of explaining what it means when you're doing this measurement and influencing something.
That could just be like a subsection of the multiverse. There could be another like completely different subsection where you have a different hair color for some reason and you just make the exact same decisions that you've made, but something's different about you. But I love the split in timelines description in media because that just reminds me of that Rick and Morty episode where there's any sense of uncertainty, like space-time splits and they enter different universes. Because I think that's what I think whenever I think of the multiverse. I don't think of Doctor Strange. I don't think of Marvel. I think of Rick and Morty. So maybe I'm never going to get that out of my head. Maybe that's just like the way I thought about it. And that's just the way it's going to stay.
I feel like that means that anyone that is slightly uncertain, or I guess maybe not so confident in life, is just always confused because they're always splitting into many different universes.
Yeah.
Whereas someone who is always certain of what they're doing has one path and that's it.
Yeah. Yeah. That's a good point, actually. Maybe if you're more certain, then you have like a shorter path through space time or something. I don't know. That's getting confusing now, though.
I feel like we're going down some sort of just general philosophy route and veering away from the maths of it and just thinking about, well, what happens if I do this?
Yeah, yeah. The maths is hard though. It's the philosophy that's the fun thinking point. But I feel like we were going down the cosmology route because that's all about like different universes, light paths where you go, how long you spend in a certain area and how much time that passes for you. That feels very cosmology relativity for me. So maybe that's why I'm getting confused. Let's stick to the maths of quantum mechanics.
All right. So I've got this idea that if we go back to sort of my undergrad physics, you have a particle in a box. You've done something to it to try and take a measurement, and then that sort of makes you split into one of the multiverses.
Yeah. And that's one theory of multiverses as well. Like if we're assuming that this many worlds is right, then that's what happens. Which is what it was in a lecture to some students. Schrodinger said, like a preface of what I'm going to tell you, you're not going to believe. And it's that everything that we can look at and think of already exists in some area, and that area is a different universe. I think it's an idea that I feel like I can get behind. Like, can I do the maths behind proving it? No, but there's something about it that I like.
It just intuitively makes sense. It makes you comfortable with the universe that we're in.
But maybe that is just because that's like what media just always goes through. But I do think it's interesting how the multiverse like got mentioned in one Marvel film a few years ago, and now you have like films based entirely on the multiverse. Like, I don't know how much more research on the multiverse has been done in that time, or if, I don't know, some writers at Marvel just like saw it somewhere and decided to include it. But I wonder if it's getting a more relevant part of science. I don't know if it's getting to that like exciting part of physics. For example, people growing up in the 50s hearing about a possible like moon landing is like, I don't know. I don't think we're gonna get any evidence for multiverses, but is that where physics is going, to like always trying to find something that seems like out of reach?
I kind of feel like it has to if it's always talking about these theories. And as science, it doesn't necessarily become more and more complex, but you need more multidisciplinary teams to move science forwards.
Yeah.
Because you can't just look at anything from one particular angle. Like even some of the like material science work that I've been involved in, it's involved like people that understand physics, people that do data science, people that understand chemistry, all of them coming together, and people that sort of understand how radiation works to look at things.
Yeah.
So I feel like, yeah, physics is always going to be sort of pushing that boundary because it's all the maths that it's sort of trying to understand how everything fits together, isn't it? Using maths.
That's why people, I mean, you mentioned like a grand unified theory, and that's, I guess, maybe in a bit more particularly because you have the four fundamental forces, and three of them just, they're perfect. Like they make sense. They fit into the standard model, which people know is wrong because of dark matter and dark energy doesn't really fit in. But anyways,
just ignore that jargon.
Yeah. Anyways, so there's that. Obviously, the standard model doesn't work. But because they know that it's not the most perfect model, because it doesn't include gravity, it doesn't include the fourth fundamental force. And so a lot of people are trying to search for this theory beyond the standard model that includes everything that works from the standard model with gravity as well. Because currently it's like separate. And when we did a module on it, we did about the standard model for 9 out of 12 weeks. Well, more than that. It was probably like 10 or 11. And then the final few weeks were on beyond the standard model. And then it was all these crazy things that could happen and would, if this happened and they found this, then it would explain all of this. And so I think people are always constantly searching to kind of, one, figure out the unknowns, but two, figure out what the unknowns can tell us, because it's kind of searching for the unknown unknowns in a way, which I think is cool, but also feels so tiring.
To me, science is about finding out something and reaching a conclusion and moving forward, because that's what you do in school. You do an experiment and you get a conclusion. And then when you get to physics, like the theoretical physics, like, yeah, we don't really do that. We just keep coming up with new theories and then trying to figure out ways of testing them. How do you measure something that you can't directly interact with?
Yeah, well, that's what all of the particle experiments, I think, they when there's a new particle that gets theorized, they design experiments specifically searching for it. And then it's always like, I mean, I don't know how particle physics like do it, because it's just searching for like this this little bump that just means like the Higgs particle exists. And I think that's really cool. But I feel like my area of physics that I like is like application heavy. I want to do something, solve something, and then a very quick turnaround. I want to see how that's going to help something. I don't know. That's what I've realized doing physics. I'm like, I really can appreciate the theorists. And I think they are just crazy intelligent. And I like reading about the theory stuff. But as soon as it goes into, how do we actually solve this? I'm like, no, I'd rather be able to see my solutions and see how, what contribution they make. So maybe it's just the different types of people just think different parts of physics are more valuable and more important than others. But that's just biases, really, I think.
Yeah, I guess that depends on your viewpoint, because I would imagine that some of these theories have led to some great discoveries. And I was reading about the whole quantum entanglement thing. That is how like quantum encryption works, isn't it? Which
Mm-hmm.
is how some data security is done.
Stuff like quantum encryption, people years ago would have thought, well, that's crazy. And it sounds just like some people say to sound like physicsy. But now people are actually trying to get quantum encryption to work on like a global scale so that when you have your bank details, if you encrypt them using a quantum computer, whenever somebody tries to steal them or hack them or take that information, it just destroys the information. And then it's physically impossible to kind of steal and hack into something, because currently I think they do encryption on like secure details so that it takes a supercomputer 100 years to crack it. But like the idea is that it's crackable. And so now we're moving into using quantum computers to try and have like a key and a lock system. If you lock something with a specific key, then only with that key can you unlock it. And that's a bit quantum encryption. And if somebody tries to, break the lock, then it just breaks and you can't open, which I think is cool that it's actually getting an application, because that's something that's quite theoretical that's now being found to be useful on the global scale. Because when you tell that to people, they're like, a supercomputer takes 100 years to break into my details. No. And everyone's like, nothing's secure. It's obviously good enough for now, but I think as well that as like technology advances, how much is that time going to be broken down? Like how good can supercomputers get before we need to use quantum computers?
No, and I guess if we keep looking into the future, this is what I find weird about most representations of like time travel in films. They start hopping around through time and affecting their original timeline. But I feel like if so, this is one of the things with string theory where you get so far down the dimensions, you can go back and forward in time. But I feel like you won't affect the timeline you're originally in because there are all these multiple timelines anyway. So
Yeah,
it's like you were
yeah.
saying that everything is happening anyway.
I've never thought about it like that, because I always think, with time travel films, they always say things like you can't change things because, the butterfly effects. At the end of the day, somebody won't be born. I mean, you might not be born, but I've never thought about it as they go back in time to a different universe that was the same at that point.
Yeah, that's what I tend to think of. I mean, I kind of suspend like my normal thinking when I watch a lot of films that try and incorporate science.
Oh yeah, to try and enjoy them, honestly. Wait, what is it on Back to the Future when he goes back and then changes something, then he goes back to the future and everything's changed? How does he fix that situation? Does he go back and undo things?
Yeah, so he ends up with sort of like three versions of himself running around, doesn't he? There's like, or is his self from like a previous film doing something,
Okay.
and then the other version of himself, and then his current I think maybe I'm misremembering it. Maybe I have to rewatch Back to the Future. But yeah, he was basically trying to avoid running into himself, wasn't he, at every point?
Yeah, because I would say if he went back and then he changed the future, surely he could. I mean, if he could travel between multiverses, go to a different universe where he never changed anything at all, because that would theoretically exist.
It would, but it would make for a very boring movie plot.
Yeah, yeah. I think they have a plot line like that in Rick and Morty as well. There's like a universe where they die, or they go back in time, they die, and then the future them buries the past them. And then there's just like an area, not an area. a scene where they point at like these holes in the ground and they go, that's where we're buried. And it's kind of like crazy like thought experiment on how timelines work, which is maybe honestly, like, you don't even need to do a physics degree, you just need to watch Rick and Morty and Back to the Future for the time, understand the timelines.
Yeah, and then decide for yourself if you think this is actually feasible, and then come up with a new theory.
Yeah. Maybe more physicists need to work on these shows and then just try and animate all the different theories that are possible and just see what the reaction is from people.
I think there'd be a lot of confused faces, but you never know. Maybe someone will hit on some way of explaining it that is 100% accurate and easy to visualize.
It's true.
So you were talking about non-linearity before, and some things are and some things aren't. Can you sort of explain what that means? Because I think of it as a cause has an effect, and that's linear. You go from A to B. Is that what you mean?
Kind of. Because a cause does have an effect, but it's like a cause with a slightly different change has a huge change in that final effect. And I get that is essentially what chaos is. It's just these like tiny changes in initial conditions that result in huge changes in the final results. And non-linearity is actually just, I think I did a module on it, and it's just a really cool concept. Like, you get loads of strange and weird things happening when you have non-linear things happening in the universe, which happens, even just with like gene regulation and everything like that. That's all non-linear. Like, it happens in biology. It's not just like, that's what I like about some areas of maths and physics, is you can see that they happen in actual biological systems and in nature. So some people think that non-linearity is a very abstract concept that doesn't have many kind of applications, but it's been existing in nature for a while. I don't know if I've gone very off topic here.
Oh, so the reason I was asking was because we were talking about films, right?
Mm-hmm.
And there's a film on Netflix at the minute called Look Both Ways, where someone who is just about to graduate from university, she takes a pregnancy test. There's one timeline where it is positive and she has the child, and there's another timeline where it's negative and she goes to pursue her career.
Yeah.
But they both end up pretty much at the same point at the end. It seemed like it didn't really matter what happened in her life. She was always destined to have this career and have a family. It didn't really matter how she got there.
Well, I guess, okay, in that context, that's a very linear timeline, because I would say it's like the butterfly effect, though. Essentially, like, non-linear is when you have like the changes. And so I feel like if it was non-linear, if it was realistic, then she wouldn't be ended up in the same place. People always love non-linear stuff in films, and now there's a film that's linear. I don't know how I feel about that, because I wouldn't say that would be a talking point.
I quite liked it. It kind of said, like, it doesn't really matter if you don't do something great first time necessarily. You'll get there in the end.
It's a nice little thought, actually. Maybe they did it for the post-film thoughts and morals, where you can get in a bit more confidence and be like, yeah, it's going to be okay, rather than you make a change and just everything descends into chaos, which is exactly what the physics would say.
Exactly. And I find that really disconcerting, this idea that this small change can have this huge effect that could fundamentally change my life as I know it.
Yeah, that's how they actually do like weather modeling sometimes as well, is like when they have a measurement and they have the forecast at that point, they see how different it is and they try and model it to be as close as possible, because if there's like a big enough change and difference, it means that your forecast for 3 days time is totally different than what it's actually going to be in 3 days time, even when you use a model. So that's why I learned, if you ever want to know what the forecast is, you just have to look the day before, because it gets to like 6 or 7 days in advance. And because of the differences in the model and what's actually going to happen, it just becomes so different. It's almost like, what's the point of putting a forecast up?
I think that brings us back to probabilities as well, doesn't it?
Yeah.
They always say there's like a 20% chance of rain or a 50% chance of rain, and I always think 50% chance is just normal around here. That just means it probably won't rain, but be prepared anyway.
It's really interesting how you interpret those probabilities as well, because when somebody says 20% chance of rain, I always think probably not going to rain.
And then it does, and you say they're wrong.
But if somebody said 100% chance, and you're like, is that it's raining now? Is that, I don't know, because can anything be 100% in the future? Because there's definitely some times when you look at a forecast and it says 5 p.m. or 100% chance of rain.
I feel like we're saying that weather forecasting relies on some really complicated physics and maybe
Yeah.
involves a multiverse.
Everything involves the multiverse if you try hard enough.
I feel like we're kind of getting hideously distracted and confused by sort of real world things like forecasting the weather and things that don't really happen but only happen in the movies, with some physics that again also it doesn't really happen but it's just what people think could be possible.
Mhm.
That's what I'm getting out of this episode, but I feel like I still don't quite understand it well enough to sum up very well. So do you want to try and conclude this episode, Emma?
Sure. Oh, I can say a very cool quote actually. It's a Feynman quote, and this is hopefully to put everybody at a bit of rest, a bit of ease. And simply, it's if you think you understand quantum mechanics, then you don't understand quantum mechanics. That's where I think it's a good place to end it. Is there's many things that could happen, and the multiverse theory I think is a really cool theory to think about, and that's why it always gets put in all these films and everything like that, which is interesting and cool. But when it actually comes to the maths of it, that's when things start to get really confusing. You have all these different theories pop up to trying to fit the theory into the maths. And so I think do a quantum mechanics physics course, and then you'll see the maths, and then you'll be like, yeah, and then you'll think about multiverses, and then you'll be back to square one again. So that's probably the best way to end it.
Fair enough. And as Richard Feynman said, you'll probably never reach that understanding because it's weird, man.
Yeah, it really is.
Cool. Thank you for that summary. If you're still listening to this and you like what you've heard and you want to support this podcast, we would really appreciate it if you would follow the link in our podcast description and maybe consider buying us a coffee. So we'd really appreciate your support, and it's always really nice to see people interacting with us as well. So go check that link out, and we'll see you next time. The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.